Good morning. My name is Isaac Alvarez, and I am presenting on a study focusing on artificial blood vessels, specifically analyzing flow simulations and static simulations to approximate that environment, and then evaluating that biomechanical criteria as well as the economic criteria to find an achieved optimal design material. So to give some historical context, cardiovascular disease has impacted humanity for a while and has and continues to prompt active development towards artificial blood vessels, but did start in the 1900s with an Austro-German surgeon who attempted to implant a magnesium tube, unfortunately induced pneumonia in the patient and they died 3 days later, but it did catalyze the movement for this type of development. Fast forward to 1985, largely more successful, specifically synthetic materials being implanted, but they were limited to large diameter vessels. Hybrid grafts also were up and coming, but again, limited to canine models or just animal models in general. Fast forward to 2000s/present time, tissue engineered vascular grafts, cellulized vessels, very much active and adamant focus for solutions to develop these artificial blood vessels. So in terms of design parameters for my model, I chose to focus on the common carotid artery, or the CCA, especially in light of carotid artery disease, which involves clogging and plaquing, clogging from plaque, which results in occlusions or narrowing of the vessel. And anytime this blood flow is restricted to the brain, which it does connect to, you risk a stroke occurring, which is in fact the leading cause of death within the United States. So in terms of building my model for the CCA, the parameters were relatively straightforward. Found my diameter, my thickness, and my flow rates for the average male. So before building this model, however, I had to limit some material options. Here, TEVG, synthetic, natural, and hybrid were the alternatives. From the get-go, TEVGs did have those very strong benefits of tailored compatibility, biodegradability, and structure, but the risks did outweigh the benefits in this case, as there was limited research, and from reported studies, it's very high failure rates for human use. So that left synthetic, natural, and hybrid. Synthetic, of course, maximizing simplicity, mass reproducibility, but very poor compatibility for long-term use. Natural exhibiting the opposite behavior with excellent compatibility, but lacking strength, and it's easily degradable. And hybrid, of course, being the nice blending of the two, so optimizing those benefits. I ended up establishing three, ePTFE and PET being my two synthetic materials, and they are standard for artificial vessels with larger diameters, and hybrid, of course, being PCl, which is synthetic material with chitosan, a natural material. So here are the corresponding mechanical properties with elastic moduli, Poisson's ratios, density, and yield stress to run static simulations later on. And constructing my model, of course, the materials did not change the dimensioning, but the constant diameter with constant thickness, and I wanted to look at 3 different lengths before I ran my simulations. So initially, that flow simulation did have some parameters I needed to configure initially. Blood, of course, being our working fluid, and gravity opposing that fluid direction since I'm looking at the CCA, and so it's directly opposing that vertical flow to the brain. Our ambient conditions, of course, involved average body temperature, and the boundary condition was that diastolic blood pressure that we're expecting at the outlet, since it's going to be directly preceding when the heart is pumping that blood. So again, more configuring for the flow simulation. Used a high mesh to increase that computational accuracy, but it was important to note that the material properties are neglected in this flow simulation. So a total of 6 flow simulation trials, the 3 lengths I wanted to investigate, and 2 flow rates for each length, normal flow, and a worst case scenario type situation where you had 5 times that normal flow. And here were the corresponding pressure outputs, found that maximum pressure for each respective length, and the different flow rates. Those pressures I did apply as internal pressures inside this artery once I started up my static simulation, but before running it, I had to fix the supports at the inlet and outlet faces respectively. And lastly, I accounted for total pressure as opposed to the gauge pressure seen earlier so that I could account for atmospheric pressure applying on the external surface of the artery. Here are the trials for the flow rates and the lengths, a lot of data for our stress and strain. But across the materials, it did give the ability to be compared. So specifically discussing said results, initially those pressures, you can see that there's no trend for the lengths changing, but pressure did increase with flow rate, which did align with our worst case scenario type situation. For stress and strain, the distribution occurred along the edges of the artery, which did align with stress concentration. And lastly, those stress and strain values specifically did not exhibit a trend for changing flow rates, but you can see that they increased with length. Comparing the materials, however, did more so correlate with their mechanical properties that I previously inputted. Here you can see that there was no material that exceeded the yield stress, which was very significant because with von Mises, if it exceeds the yield stress, that means it plastically deforms. So none of them did. They would all return to their original shape. Strain, interestingly, EPTFE and PCL chitosan did have the exact same strain, but that is likely because of the same Poisson's ratios. And lastly, evidently, PET was the best performing in this case. So for our final product recommendation, the engineering criteria was important to evaluate first. Here I focused on the fact that common arterial vessel failures are because of restenosis, which is the narrowing of the vessel, as well as thrombosis, which is the coagulation of the blood, clotting, very high risk, very detrimental to the longevity of the vessel. And so here the goal was to minimize the mechanical loads, which may induce damage, which may cause thrombosis. So essentially by minimizing those mechanical loads and maximizing how well it performs, you potentially minimize those risks. And PET did perform the best in this case. For economic criteria, however, I found the price per unit volume and was able to compute the exact cost for constructing a 100 millimeter CCA model. In this case, ePTFE was the most cost efficient. But before coming to that final conclusion, it was important to address some errors. Here we simplified those flow parameters initially. Maybe you could have had some blood viscosity values accounted for slip condition, maybe even the arterial wall properties. For estimating, did estimate those material properties. It was very hard to find established values, especially since there's limited research and studies for the specific application of these materials in artificial blood vessels. And of course, the sources I did find, it did vary between application and context of what this material was being used for. And lastly, the limitation was on those material properties, only accounted for 4, potentially could have increased the static simulation accuracy if I had included more mechanical properties in those preset material settings. Some general improvements that were interesting to consider would have been comparing that implant versus the native arterial tissue, seeing if the mechanical behavior to those loads did align, because that is a very serious cause of the complications whenever there's that mismatch. And secondly, another alternative improvement could have been with the model changing to incorporate plaque so that you had blood flow maybe inhibited as you ran that flow simulation and seeing those corresponding mechanical loads. So conclusively, for the final product recommendation, I was looking at the context of mitigating clinical risks, minimizing those hazards because the patient safety comes first. So durability, biocompatibility, seeing how it mechanically performed was very important in this case because minimizing damage did outweigh the slight increase in cost. And so therefore, PET was the best performing in those criteria and was the final product that I would recommend. Thank you.